At this level of calculus, we've seen a lot of recurring ideas that really it boils down to a simple change of variables. So what do I mean here? Well, let's think back to our first calculus course when we learned how to take U substitution and use this method to solve integrals, right? What is U substitution? Well, you start with an integral. Maybe it has bounds, x goes from a to b, of some function dx. We make a sub that u equals something, and then du equals the derivative of that something dx, right? And then what do we get? Well, then we also have to change the bounds. Well, then we get an integral that's u goes from a to b, and now we have some function in the variable u, right? Or maybe even we could just say f of u du. This is a change of variables, right? We started with the variable x, and we said, okay, this integral is difficult in the variable x. I can make this proper substitution with the variable that we call u, and make this an integral that's not so difficult. What else do we do this in? Well, another example is something we've seen in this calculus course is like take a double integral. Say we have a double integral over some region R of a function f of xy dA, and we can convert this to polar coordinates. So let's say like rectangular to polar. If we do this, then the integral is over some region S, we'll say, like this region R written in polar coordinates, we'll call it S, of, and then we look at our function in the variables r and theta, and then we have r dr d theta, right? This was also a change of variables because we let x be r cosine theta, and we let y be r sine theta, right? And so we take this change of variables, and the hope is that however difficult this integral was on the left here, the entire goal of change of variables is that the integration becomes easier. And you say, okay, well, I would rather spend the time and effort substituting these variables. That's going to be less work than trying to solve this in its original variables. And so these are all ideas, right? You know, we've done cylindrical, we've done like rectangular to cylindrical, rectangular to spherical, or you can do spherical to cylindrical and vice versa, right? These are all examples of transformations. So let me write here. These are all examples of what we say in the more general setting. We call these transformations. Okay. And let's look at first just planar transformations. These planar transformations involve taking a two-dimensional region to a two-dimensional region. So let's imagine here we have, let's say we're in the UV plane, and we want to transform this to the XY plane. So what a transformation does, we'll call this transformation T, is it takes some region. So imagine we have this region here, we can call it G. And it takes a point UV, and it maps it, we use the terminology maps, it maps it to maybe some region R in the XY plane, where here we'll say T of UV equals XY, right? And so T maps the point UV to XY. And then it comes with descriptions of what this transformation is doing. So we could say x is equal to some function in u and v, and y is equal to some function, we'll say h, of u of v. And this determines the transformation. So t is determined by these equations here. This tells us how it's taking a point uv in the uv plane, and where is it going to send it in the xy plane, right? And I want to quickly make a note about a requirement that we'll impose, and it'll be clear why we impose this requirement in a little bit. But we're going to require that the first partial derivatives exist, so that like gu, gv, h sub u, and h sub v, we're going to require that these all exist. Again, we'll see why in a little bit, but for now, let's get that boilerplate statement out of the way. And there's also some notation we can introduce here. So this is a map or a function from the domain G to the region R. And some notation here is we say T maps G into R, or T maps G to R. So this notation in English, T maps G to R, or T sends G to R, or T is a function with domain G and we'll say range R, right? These are all ways that we can think about this notation here. But for shorthand, I'll usually just say T maps G to R. And now let's introduce a definition now that we know what a transformation is, right? It takes some domain here, and it alters it in a specific way based on a family of equations. So let's introduce a definition now, and it's a type of transformation. So we say a transformation T from G to R given by T of uv equals xy is 1-to-1, or the terminology I'll use, they're both used probably just as much as the other, but the one I'll be using is the word injective. So we say a transformation is 1-to-1 or injective if no 2 points in G map to the same image point in R. So a function that sends no 2 points. So if you can imagine here, we have G. Let's say over here, we have R, right? A function is 1-to-1 if for any 2 distinct points here, they get sent to different points in R, right? So this is an example of injective. Now, if we had something like, here's G, here's R, and if we had 2 points under the transformation T here, so I should say, this is T that maps G to R. Under the transformation T here, if we had that these 2 points got sent to the same point, this is not injective or not one-to-one. And here the terminology one-to-one makes more sense, right? Because here you can see it's one-to-one. For every point in the domain, it has its own image, right? Here, there are 2 points in the domain that have the same image, right? That's not one-to-one, that's 2-to-1, right? Because 2 points are going to 1 point. So that's 2-to-1. 1-to-1 or injective is when every point is mapped to its own image point. And so let's look at like maybe some more serious examples here. Let's look at an example of an injective function. And we can look at f going from the real numbers to the real numbers given by f of x equals x cubed. Okay, this is a function that we've been working with since probably middle school. So we have x cubed here, snakes kind of like this. So this is f of x equals x cubed, right? And now how do you check injectivity, or how do you check if this is one-to-one? Well, you pick points in the domain. So the horizontal, the x-axis is our domain, right? This is the x-axis. And then the real numbers, that's the range, is our y-axis, right? Because that's what a function is doing, is you plug in an x value, and so we pick an x value, and we see if there are any other y values at that level. And so you could take like a line through here, and we see this is unique, right? This red line that I've drawn intersects the curve y equals x cubed nowhere else, right? Because if I pick a point over here, well, then its image is all the way off the screen. So maybe I'll pick one that's a little closer right here. And so you can see this intersection is always unique. And so that means, like, for the example of a function from the real numbers to the real numbers, f of x equals x cubed is an injective function. Let's see something that's not injective. Something that's not injective, well, again, we can look at f from r to r, from the real numbers to the real numbers, given by f of x equals x squared. Well, if we look at x squared, imagine that's centered at the origin there. If we pick a certain x value, there's a corresponding y value here, right? So say we pick, well, if you pick x, you get the value x squared here. But you can also pick the value negative x and still land at the value x squared. And so because of that, this function is not injective. 2 points, x and negative x, both map to x squared, which means this is not injective. It's not one-to-one, because there are 2 x values, right, that map to the same point. There are 2 points you can pick on the x-axis that land you at the same point on the y-axis. This is not injective, or it is not one-to-one. And here now, maybe you can start to get a better idea of injective versus non-injective, or one-to-one versus not one-to-one, based on some of these examples. And so this is intuition, right? When functions are simple enough, you can determine injectivity almost based on intuition. Obviously, you need to prove it rigorously, right? And so for here, you know, like for x squared, to prove it's not injective, we picked 2 points on the x-axis and showed or proved that they mapped to the same point, right? That's proving that it's not injective. To prove it's injective, you have to show that for every single point, its image is unique. Well, there's an easier way we can do this in general. So, how to prove a function is injective, or again, one-to-one. Well, let's imagine we have t goes from G to R given by t of, whoops, I don't know what I'm doing with that parenthesis there, given by t of uv equals xy. So let's say we have this transformation t, and let's assume, so to prove something is injective, here's your hypothesis. You assume that t of u1 v1 is equal to t of u2 v2. So what you have is, so here's G, our map T, some region R, right? And you pick 2 points such that their image is the same over here. So T of u1 v1 equals T of u2 v2. So you set this equality here. So say that this is u1 v1 and this is u2 v2 here. And then try to prove that u1 v1 was actually the same point all along as u2 v2. This is what it means for a function to be injective. So it's injective if you assume that the point in the range is the same. Well, then you have to kind of work backwards and prove that they were actually the same point, right? This is what it means for it to be injective, because if these were the same point, then this point in the image was unique. But if you can construct a counterexample, for example, if you can find points u1, v1, and u2, v2 where they were actually different, well, then that tells you that it's not injective, right? But it is injective if you can assume that t of u1, v1 is equal to t of u2, v2, and then you can prove that u1, v1, and u2, v2 were the same point. Okay. And so another way to think about this is maybe a little more intuitively, or a little less kind of clouded here, is just the simple statement that t of u1, v1 equals t of u2, v2 implies that u1, v1 equals u2, v2. So t is injective if this statement here, if the points in the range being the same implies that the points in the domain were the same. So let's see some examples. Let's look at the examples that we were given here, right? We did f of x equals x cubed, right? This was one example we had. Well, let's assume that f of x1 equals f of x2, right? Well then, based on this assumption, since we have f of x equals x cubed, then that implies that x1 cubed is equal to x2 cubed, Well, then we take the cubed root of both sides and get that x1 is equal to x2, right? And so this was injective. However, if we were to look at f of x equals x squared, and then we were to assume that f of x1 equals f of x2, then we'd have that x1 squared is equal to x2 squared. But when we take the square root here, so when we take the square root, we know that we get x1 is equal to plus or minus x2. This is not injective, since we can have that x1 equals negative x2. And this assumption still hold true, right? This assumption can still be true if x1 equals negative x2. And so because of that, we see it's not injective. So let's do now a little more general example here. Maybe something that's, so this has been one-dimensional, right? Because we're looking at functions that go from a one-dimensional space to a one-dimensional space. Let's look at a function that goes from a two-dimensional space to a two-dimensional space. So let's consider t of r theta equals xy given by x equals r cosine theta, y equals r sine theta, right? Now let's find the image of g equals r theta such that r is between 0 and 1, theta is between 0 and pi over 2. And then we're also going to ask, is t 1 to 1? Or injective, right? Well, first let's just calculate the image, right? Let's find what the image of this transformation is, and then we can discuss if it's 1 to 1 or not. So we have g is in the r theta plane is between 0 and 1 and 0 and pi over 2. And so for g, we have the r theta plane here. Let's make that a little shorter. R goes from 0 to 1, and theta goes from 0 to pi over 2. And so in the r theta plane, this is a rectangle, right, of length 1, height pi over 2. And now under the transformation t, we want to understand what this is in the xy plane, right? Well, if r, let's remember what our transformation is. It's x equals r cosine theta, y equals r sine theta, right? Well, we know what theta going from 0 to pi over 2 means. Theta going from 0 to pi over 2 means that we're in the first quadrant here. And then r going from 0 to 1 means, well, we start at 0, and then when r equals 1, this is to say x squared plus y squared equals 1. And so this is a circle of radius 1, but we're bounded between theta equals 0 and theta equals pi over 2. And so the image of this transformation is this quarter circle of radius 1. And so we can say this is r. We haven't really specified here. Let's say t goes from g to r. And so the image here is this quarter circle. right? Which is how we're used to seeing this set G between R0, 1, theta between 0 and pi. But in the R theta plane, right, this is actually a rectangle. And when we understand this set of R going between 0 and 1 and theta going between 0 and pi over 2, we've always pictured it as this semicircle, or this quarter circle, excuse me. It's much more intuitive to consider it this way, since we have learned most math in the XY coordinate system, right? But here's an example of a transformation that kind of behind the scenes we've always been familiar with, right? Now let's show if this is injective. To check injectivity, we want to assume that T of R1 theta 1 equals T of R2 theta 2, right? Well, what does this mean? If X is R cosine theta and Y is R sine theta, and we're assuming that these points are equal in the image, well, then that's to say that R1 cosine theta 1 is equal to R2 cosine theta 2 and R2 sine R1 sine theta 1 equals R2 sine theta 2, right? We can see that's what it means for R1 or T of R1 theta 1 to be equal to T of R2 theta 2. Well, you just look at the X and the Y values, right? This is equal to, if you'd like, this would be equal to like X1, Y1, and this would be equal to X2, Y2. Well, then you're assuming those are equal, but then, so X1 is equal to X2 would give you the top equation here, right? This is X1 equals X2, and then the bottom equation would come from Y1 equals Y2, right? And so now you want to try to argue that R1 must equal R2 and theta 1 must equal theta 2, right? So we can kind of cross multiply and cross divide here, and this system of equations will give us that R1 cosine theta 1 over R1 sine theta 1 is equal to R2 cosine theta 2 divided by R2 sine theta 2, right? Well, you can cancel the R1s and the R2s and then get that cosine of theta 1 over sine of theta 1 is equal to cosine theta 2 over sine theta 2, right? Well, so this is saying that the cotangents are equal, but that's the same as saying that the tangents are equal. So this tells me that tangent of theta 1 is equal to tangent of theta 2. And now from here, we need to look at the graph of tangent, right? Remember, we're between 0 and pi over 2 in our theta bounds. And over the interval 0 pi over 2, graph of tangent does something like this, and it's injective, right? So we need to know that tangent is injective over the interval 0 to pi over 2. And because of that, well, then we know that theta 1 is equal to theta 2. So this gets us our theta equality. And then you can take this theta equality, plug it back in all the way up to both of these equations, right? If you plug in that theta 1 equals theta 2, well, then immediately you get that R1 equals R2. And so this implies that R1 equals R2. And because we have both of these, this means that T is 1 to 1. Okay, so here's an example of calculating the image of a transformation and determining if it's injective or not. So I want to make a remark here about functions that are injective or one-to-one. If t is one-to-one in R. So let's say we have t going from R to S now, right? And if it's one-to-one in R, meaning it's one-to-one on its domain, then the inverse, T inverse, which goes from S to R, exists. And we have some identity relations. We have that T composed T inverse is going to be the same as the identity function on S, right? Because what is the identity function on S doing? The identity function on S is going to be a map from S to S given by, you'd say like the identity of S of, let's say Y equals Y, right? The identity map is the one that sends a point. So it's the map where the domain and the image are the same, or the domain and the range are the same. And it just maps everything to itself. So like Y goes to Y. And then we also have that T inverse composed T is equal to the identity on R, which goes from R to R. And again, the identity on R would be you take a point and map it to itself. So this is a quick remark that I wanted to sneak in here. The last thing I want to do for this video is an example, a little more difficult example of finding images. Here we kind of use previous knowledge to determine what an image would be, right? Let's do one where we kind of have to calculate everything ourselves. So let's take T, let's consider the transformation T of uv equals xy, where x equals u squared minus v squared, and y equals uv. Okay, let's find the image of the triangle in the uv plane with vertices 0, 0, 0, 1, 1, 1. Okay, and so what are we looking at here? We have the UV plane. We have the triangle with edges 0, 0, 0, 1, 1, 1. So here's our domain. We want to map this under the transformation T to the XY plane and get something, right? And the question is, what is this something? Okay, so what you always want to do with problems like this is you want to see where the vertices map to, and then you want to see where the sides map to. Once you do that, you can check where the interior will go. So kind of always check vertices and sides. So what do we have for the vertices? Well, for the vertices, we need to check T of 0, 0. We need to check T of 0, 1, and we need to check T of 1, 1. And let's use a page here to keep track of our picture. As we go through checking everything here. Okay, so we're starting with the point 0, 0. 0, 0, well, x equals u squared minus v squared, and y equals uv. And so let's keep track of that as well. X equals u squared minus v squared, y equals uv. If we plug in the point 0, 0, we're going to get 0 squared minus 0 squared for x, and then for y, we'll get 0 times 0, which is the point 0, 0. So the origin maps to the origin, right? We can have, let's indicate our vertices in red. And this is t of 0, 0. Let's check the point 0, 1. Well, if we check the point 0, 1, u is 0 and v is 1. So we have 0 squared minus 1 squared, and then we have 0 times 1, which looks like it's going to be the point -1, 0. So the point 0, 1 mapped to the point -1, 0. This was t of 0, 1, which is -1, 0, right? And so we're seeing piece by piece how this transformation is behaving. So what do we have next? Next we have 1, 1. So x is going to be 1 squared minus 1 squared, and then y is going to be 1 times 1, and so we're going to get the point 0, 1. So the point 1, 1 mapped to the point 0, 1. This is t of 1, 1, which is 0, 1, right? And t of 0, 0 was 0, 0. Okay, and so now we've checked the vertices. Let's check the sides now, right? So the vertices, check. We figured out where those map. Now let's check the sides. And we can label our sides here. Let me draw the rest of our domain. So if we label these sides A, the leftmost, B, the hypotenuse, and then C, the top of the triangle here, we can see what happens to each of these sides, right? And so, whoops, where are we going? So let's see what happens to side A. So we need a way to describe what side A is doing. Well, if you notice, side A, if you're a point on the line, U is always 0, right? I should label my axes here. U is always 0, and V can alter between 0 and 1. So side A is the set of points such that U is equal to 0, and then V is between 0 and 1. Well, then to plug this in, we're just going to check T of 0V, right? Because U is always 0 on this line. Well, that's 0 squared minus V squared, because remember, x is U squared minus V squared, and then Y is U times V. So we have 0 times V, which gives us the point -V squared, 0. And V is between 0 and 1. And so this means that -V squared is between -1 and 0. And if we come to the picture here, that means side A is mapped to this -V squared, 0, right? Where V is ranging between 0 and 1. Well, if we're between -1 and 0, and for the x component, and we're always 0 for the y component, well, that's this line right here, right? This is the image of A, so we'll say T of A. Because again, the x component is a negative value between 0 and 1, right? or it's a value between -1 and 0. The y component is always 0, which exactly gives us this line segment. You can see any x value here is going to be between 0 and -1, and then any y value is 0. And so this is where A mapped. Let's look at what happens to side B. Okay, side B, we need to look at this hypotenuse here. Well, here, B, we can express this in the UV plane as an equation of slope 1. So here we have that U can be between 0 and 1. And then for V, well, it's just the line V equals U, right? That's what this equation is, going from 0, 0 to 1, 1. Well, U can be between 0 and 1, and then we're on the line V equals U. And so let's see what T of U comma U gives us. Well, that gives us U squared minus U squared, and then U times U, right? Which is 0 U squared, where U is between 0 and 1. And if U is between 0 and 1, U squared is between 0 and 1. And then so here what we have is that the x values are always 0, and the y values are something between 0 and 1. And so because of that, something where the x values are always 0 and y is between 0 and 1. Well, that's this interval right here, and we'll call this T of B, between the two vertices, 0, 0 and 0, 1. And lastly, let's see about side C. Well, side C here, V is constantly 1, and then U ranges between 0 and 1. So for side C, we have that U is between 0 and 1, and then V is constantly 1, right? And so what is T of U1 going to give us? Well, that's going to give us U squared minus 1, comma, U, right? Whoops. Because, well, this is U squared minus 1 squared, and then U times 1, which is U squared minus 1, comma, U. Again, this, every time we do this calculation, it's from the definition of the transformation itself, that x is equal to U squared minus V squared, and then y is equal to UV, right? Okay. So now, what do we have? We have that x equals U squared minus 1, and y equals U. Well, we could sub in y for U back into the x equation and get that x is equal to y squared minus 1. And so this is a parabola, right? This is a parabola, or if you'd like, this is y equals root x plus 1. So either way, you can see this is a parabola that opens horizontally with a with an x-intercept -1. And so this is a parabola with x-intercept -1. This is the curve x equals y squared minus 1, right? And then I'm getting a little lengthy here on time, but to finish this up, what you do is you pick a point in the interior, see where it maps, and then you'll see that it maps to this interior. And so we get that the image of this transformation T over this triangle is this region here. And we found this just by plugging in each vertex. Remember, we plugged in every vertex and saw where it mapped to. We plugged in the sides, we saw where they mapped to. And then lastly, we plug a point in the interior and see where it maps to. And you get that this is the this is a picture of our excuse me, this is a picture of our region. And if you'd like to describe the region or the image, we can say the image of T is equal to the set of points x, y, such that, well, y is going to be between 0 and 1, and x is between, or excuse me, x is between -1 and 0, and y is between 0 and root x plus 1. You could have also described this the other way as, so I described it as a type 1 region. You could also describe it as a type 2 region. But so here's like set notation or a set representation of the image of this. And we're saying I'm calling the image, call this just M of t here. Okay, and so this is an introduction to transformations in general, particularly planar transformations. And now that we have a nice background of what these are and what they're doing, we can start to see how does integration behave under a change of variables, or what does a transformation do to integration. And so part 2 of this lecture will be defining a so-called Jacobian, and then seeing how all of this ties together to give us formulas for change of variables in multiple integration.